Welcome, fellow chemists, to the second video in the instrumental analysis series, where we will pick up mass spectrometry where I left off in the previous video. I stopped, if you do not recall, with the teaser about the small spike in the hexane spectrum at MZ87. Have you figured out what could cause some hexane molecules to be exactly one mass unit heavier? Isotopes! Of course, they are atoms made of protons, neutrons, and electrons. However, we get to ignore electrons altogether for two reasons. First, they account for an insanely small portion of an atom's mass. Protons and neutrons have approximately equal masses of 1, while the electron is about 2,000 times lighter. If I scaled the electron accordingly, it would no longer be visible to us. Second, by definition, isotopes are atoms of the same element with different numbers of neutrons. So by counting the particles in the nucleus of an atom, we can identify the isotope. With 6 protons, the element is carbon, and with 6 neutrons, we have its most common isotope, carbon-12. This means the isotope that has 7 neutrons is called carbon-13. Mass spec can detect the presence of isotopes in molecules, but what would the spectrum of pure carbon look like? It would look like this, although I must clarify I changed the y-axis to percentage. Carbon-12 is about 98.9% of all carbon atoms, with the vast majority of the remaining 1.1% being carbon-13. For those curious, radioactive carbon-14 would account for about 10 to the negative 10% of all carbon atoms, so we can ignore it. This is important information as it allows us to calculate average atomic mass, ignoring sig figs and all. However, you might be asking, how does any of this help us analyze the spectrum of hexane? Let's start by labeling the molecular ion peak as M and the one caused by the presence of the heavier isotope M+1. Based on the percentages, we would expect the height or intensity of the M+1 peak to be roughly 1.1% that of the intensity of the M peak. However, if you think the M+1 peak is larger than 1.1% of M, you're correct. The reason for this is the more carbon atoms in the molecule, the more likely one of them will be the heavier isotope. If we account for that, we get this equation. With a bit of rearrangement, we can now solve directly for the number of carbon atoms in the molecule. The intensities of the peaks are 22.4 for M and 1.5 for M+1. Put them into the equation, solve for the number of carbons, and we get, hold on here, just a moment. Yes, exactly 6, which we would expect for hexane. I hope you wrote down that equation, because you will need it later. While we can and will do more fancy math, let's apply some logic to some of the other common isotopes we may encounter. Hydrogen with 2 isotopes is a good place to start. Like carbon, one of the isotopes dominates over the other, but besides that, we can pretty much shrug our shoulders and move on. Unlike hydrogen, oxygen has 3 isotopes. We can ignore the rare O17, but there is just enough of the heaviest isotope that you might see a very tiny M+2 peak. Where it gets interesting is with chlorine. Based on its isotopes, it can only contribute to M and M+2 peaks. The interesting bit is, for chlorine, the M peak would be about 3 times the intensity of the M+2 peak. Why? Because chlorine-35 is about 3 times more abundant than chlorine-37. Similarly, bromine has 2 isotopes and can contribute to M and M+2 peaks as well. But given their abundances, what does this mean for those 2 peaks? It means they are roughly identical because the abundances are about the same. Now, both fluorine and iodine have 1 isotope, which seemingly is even worse than hydrogen. However, with respect to halogens only, if we know one is present in the molecule, a missing M+2 peak indicates it's either fluorine or iodine. If you're thinking about other elements like nitrogen, sulfur, and phosphorus, see the script for a couple of notes on them. For the rest of the video, what you see on the screen is all you need to know and apply. Now let's use this new isotope knowledge and analyze some spectra, each of which will only show the area near the molecular ion. The first will be an alkane, while the remaining 4 will be haloalkanes with each halogen appearing once. Ready? You probably regret not writing down that equation I said to earlier, but I got your back. Here are the peak intensities, so pause the video and determine the alkane. We can fill in the equation with the M and M+1 values. A quick bit of math and we get 30. Now alkanes have this general formula. The 30 we calculated is N, and using that, we get 62 hydrogens. We can check this as the M peak is at MZ422. The mass of carbon is 12, and there are 30 of them. Hydrogen has a mass of 1, and there are 62. This works out to 422, confirming our formula is the right one. Now the following spectra are all for monohalogenated alkanes. I will zoom in on each, and when I do, pause it and give it a go yourself. I will not reveal anything until every spectra has been shown. Spectrum A is pretty straightforward. The carbon calculation results in 6, which means the alkane is C6H14. We need to take away one hydrogen to make room for the halogen. And now we look at the M and M plus 2 peaks and see they are essentially the same, which is an indicator we have bromine in this molecule. The carbon calculation in spectrum B yields 12, which means the alkane is C12H26. One of those hydrogens is actually a halogen, but which one is it? Well, the mass of the M peak is the mass of the molecule, which is the sum of the masses of all atoms present, carbon, hydrogen, and unknown. Solving for the unknown reveals a mass of 127, which means this substance contains iodine. The carbon calculation is a habit by now, and there are of course 9 carbons here. The alkane would have 20 hydrogens, but this haloalkane only has 19. We can determine the missing halogen like we did before. The mass of the M peak 146 is due to the carbons, hydrogens, and unknown halogen. The unknown has a mass of 19, so this substance contains fluorine. Practice makes perfect, and we find this final example has 20 carbon atoms, which means there must also be 41 hydrogens. When comparing the M and M plus 2 peaks, we can conclude that the halogen must be chlorine because the M peak is about 3 times as big as M plus 2, giving us this final formula. Now, let me know how you did on these problems by leaving a comment below. If you felt I did not explain something clearly, definitely leave a comment below. Even if you choose not to leave a comment, thank you very much for watching. In the final mass spec video, we will look at fragmentation and functional groups.